Good morning in the west, good afternoon in the east. Welcome to the CGG Reservoir Characterization Workshop, where our theme is integrating rock physics for improved reservoir property prediction. We have some great applications of this to share with you over the next 2 days. And today we have topics on prospect de-risking, carbon storage, and simulation to seismic, all of course linked by rock physics. At CGG, we believe strongly that rock physics should be at the heart of reservoir characterization workflows. And thanks to the new virtual world that we are living in, we have assembled an expert CGG team from all around the world to show you how we do this. In addition, we are joined by some fantastic guest speakers from Norway and Milan, and from Dig Science, Rock Physics Technology, and E&I. With regard to logistics today, we will run 2 presentations back to back, and then follow this with a joint Q&A session, moderated by Ali Moradi Tarani, Regional Technical Manager for Europe and West Africa, and Brian Russell, VP of GeoSoftware. During the presentations, please submit any questions via the chat box, and we will answer these, or as many of these as we can during the Q&A sessions. And there will be an extended session at the end of the day to capture any questions that we haven't done or been able to answer previously. So let's kick things off. To start the day, it gives me great pleasure to introduce a rock physics trailblazer, someone who's been pioneering rock physics workflows for many years. Today, he will discuss with us how those workflows can help us de-risk our prospects. Please welcome Per Avseth, CTO of Dig Science. Over to you, Per.
Thank you, Mark. You see my presentation now? Presentation mode? Yeah. Okay, so thanks again for inviting me. I'm pleased to give this presentation to you today. The title, Prospect De-risking using Multi-Scenario Rock Physics and AVO Modeling. Just a brief outline. Start with a motivation or introduction, and then I'll go through a little bit the technical details and the theory behind rock physics combined with compactional modeling. And then I'm going to show how we use this to create these what we call multi-scenario rock physics and AVO visibility models. And briefly at the end, just demonstrate how we can use this de-risking prospects. And finally, summarize. Okay, I like to start the talk with this motivating figure. So this is an illustration. It could be many places around the world, but for example, in the Barents Sea, we know it's still quite a few wells drilled. It's quite complex technology. The uplift history is quite complex. So imagine that you have made a discovery, but then you have some interesting prospects away from this discovery. So one of the key questions we ask ourselves from a rock physics point of view and also from an exploration point of view, how do we extrapolate from that well to these other locations? And that's quite a tricky exercise. And it's not only done by turning on some parameters on the rock physics models. We really need to integrate with geology, basin modeling, seismic stratigraphy, and so on. And I'm going to demonstrate that to you today, that the importance of it. This is another kind of teaser slide that I'd like to show you. So to the left, you see 2 burial curves, and you see a depth or temperature profile on the vertical axis and the geological age on the horizontal axis. So the present day depth is at 0. And you have the W, that's a well location, so that's a discovery, and this is offshore Norway, northern North Sea. And let's say you have an interesting prospect, anomaly updip from that well. And of course, this is a classical challenge. How can we predict or say something about and de-risk the presence of hydrocarbons in these anomalies when we go away from wells? And the tricky thing is, of course, that as you see in the geology here, there has been some extensive exhumation that increases eastward. So it's very important to honor the fact that maybe this prospect has been deeper, but the question is how deep. And it's certainly also important to know the differences along this profile. What's the burial history at the prospect location relative to the well location? And are we seeing here just a change in diagenesis, or are we actually seeing the fluids? And that's why the compaction history and the sedimentology and the rock physics have to go hand in hand all the way. We published a paper a few years back on this technology and in the leading edge, and this is summarizing the technology. So if you have a given burial curve, let's say for the stir formation shown in the upper left, so this is the burial history, a sandstone being buried, and the brownish color is when you start to cement, so you go from a loose sediment to a consolidated rock, but then you have an extensive uplift. Then we do diagenetic modeling using the Balderhaug model for sands to model the evolution of cement volume and porosity as a function of this burial history. And these are parameters we can actually plug right into some of our popular rock physics models that we use, the contact theory-based models, the Dworkin-Ur model, and combining that with Hudson-Shrickman and Hertz-Midlin and so on. We can actually model the elastic properties, like, for example, acoustic impedance and VPVS ratio, as a function of the burial history given by this burial profile that you see in the upper left, and do Gassman to see what is the fluid sensitivity at any given location. Of course, we don't really want to know or need to know the properties back in the past, but this burial history can vary spatially, and that's why it's so interesting to see how this relates to the past. Of course, we need to also honor shale properties if we're going to look into the AVO. I'm not going too much into the details of the shale here, but we could also think that we did some physical models of shales. Those are more complex, and we tend to do more empirical data-driven studies for shales because most of the overburden and rocks are shales in silicic basins. So even if you have 5-6 wells around, you have quite a good data coverage of the shales, whereas the sands are often more sporadically located. And then, of course, at the end, you want to see how these burial trends propagate into the AVO space. Also, a very recent paper that's come out, we are showing some more examples of this, and here's a table that summarizes the strategy so here you see the different rows are different burial domains going from deposition to mechanical compaction, chemical compaction, and then uplifts. And then you have the different geological processes and geological parameters that are important to honor during these different stages, how these are related to physical parameters, and some selected rock physics strategies to model these things. And of course, there are many ways to roam, but these are some of our suggested workflows to capture those. Those are bolded out here, are actually things that we have done already, and there are, of course, things that we haven't captured yet that is important to look at also. So without further ado, I'll go to the next, show you some examples. First, I'll show you a synthetic example. Here is it's a little bit busy in terms of number of slides here, but it's quite a schematic sketch. So what you see in the upper left subplot here is a burial curve for a tertiary sandstone or sand that has been buried to a certain depth and then uplifted a little bit. But it never reached the 70 degrees onset where we know that quartz cementation tend to start. I like to call it the frying pan. It hasn't dipped into the frying pan. So it's still a loose sediment. And the porosity evolution of the sand and the shales are shown here. Then you have the cement volume in the third column, which shows 0, of course, because it hasn't been into the frying pan. And then you have the evolution of the impedances of oil and the brine sands and shales, and likewise the VPVS ratios. And then you have the crossplot of VPVS and impedance, and the AVO crossplot. You see the AVO crossplot is a little bit different here. So what have I done there? Well, actually the endpoint, which is the present day location, is kind of the expected brine and oil property of your elastic properties here in the lower left. But I can do some Monte Carlo simulation of the input parameters here and study the uncertainties associated with those parameters and how they propagate into the distribution into the AVO domain. And what we see here that even adding some uncertainties or variability in the input parameters, you see that there's a good separation between the brine class and AVO class, going from a class 2 P2 to a class 3 for the oil sand here, even though you have put in some variability. Let me now change this burial curve that you see in the upper left a little bit, and I changed it a little bit now, and you see it's a slightly older rock and it goes deeper, and you see everything change. Suddenly you have some cement in the third column here. You see it's just a few percent. It's cementing both on the way down and up, actually, as long as the temperatures are above 70. So this stiffens rock frame a lot. You lose the fluid sensitivities drastically, and you see now going back and forth you change the AVO class from 3 to a 2p-ish, 2 or maybe even 1, and there's an overlap between brine and oil sands now. So it's harder to discriminate oil and brine because of the consolidated nature of the rock. Okay, so let's have a look at some real data and see how this works. I just wanted to go back and dive into some stuff I had lying in my archives from long way back. And maybe 20 years ago, I published on this, and I just show a summary slide of the Glickner field. You see the submarine fan here with some wells penetrating that fan at different locations. And then you have some AVO observations, and you see that it's quite strong differences in the AVO responses, going from the feeder channel where you have a clear class 1, then you have a 2 to 3 in the lobe channel, and then on the margin, you're back to a class 1 again. So what's happening here is, you know, and I think what I showed in this paper is that you couldn't explain these changes just by the fluid. It was actually the phases and diagenesis was very important to account for. And let's have a further look at that. I actually did a Walderhaug modeling, combining that with rough physics for these 3 wells. And you see here that this clear trend change from mechanical compaction to chemical compaction, explaining that the sandstone data marked as black asterisks. The shales are marked with just the gray logs. And then you see that you have this kink in the velocities in all, and you're explaining that. And here we have a continuous subsidence. There's no uplift, but still, this demonstrates how important it is to honor this compaction effects. And one other interesting thing here is that the feeder channel is actually located a few hundred meters deeper than the lobe channel. You see the light blue is the top of the Heimdall formation. And the cross-plot velocity porosity here from well 3, looking through the different sand sequences, it clearly illustrate the fact of going from mechanical compaction of the shallower sands and to the cementation effect when you get into the Glickner lobe. But if you look at this map on the upper right, you see that what I did there, I just converted the contour map, the topography of the top Heimdall, into velocities using this Walderhaug function here, this black line, and converting it. And you see that the expected brine velocities are actually changing on the top of quite significantly. So there's lower velocities at the crest where you actually have the discovery well, and then it's dropping off. And of course, this is important information if you're going to do AVO analysis on the prospect, to take into account the fact that velocities and elastic properties can actually change significantly just by the fact that you are located at slightly different depths, especially if you're very near this transition from mechanical to chemical compaction. That's very important. Add to that, of course, the impact of the phases variations. So a little quick exercise demonstrating that. So here I just did this combined modeling that I just showed you in the synthetic case for the Glickner well, for the well 2. And you see here that I'm doing fluid substitution at the top reservoir, and I expect adding some Monte Carlo simulation. I see I get a clear class 2 to 3 for the oil and good separation with the brine. If I add a little bit larger depth, a few hundred meters depth, I get this one, and you see it's flipping. Suddenly you have a strong class 1 for the brine and a 2p for the oil. So you see here, this is exactly what we see in the data in this area, that the AVO responses are changing drastically just because of this differential compaction. Okay, so now I'm going to move on to this sort of bringing this more into space in the 3D, and we're going to show you an example from the Barents Sea, and the workflow is then to do this also to incorporate more of the basin modeling and geology to constrain uplifts history and combine that with AVO analysis. So here it's just a quick overview of the workflow. So we have input data as the seismic velocities. This could be FWI or stacking velocities. You have some sedimentological constraints, and then the burial history and basin history. And then we do rock physics analysis also to estimate net erosion maps and maximum burial maps. And if you have that in the first step, then you go to the next step where you use that to constrain AVO feasibility modeling in the space constrained by these maximum burial and net erosion maps. So here is from the Barents Sea, and you see in the upper left, you see the present day depth of BCU, and top Stu is just beneath that BCU. And you see here that there are some wells. This is a fingertip wells in the left side, and the right side is the hoop area wells. And of course, there were some interesting prospects in between here. We created an uplift map using the seismic velocities, and that's shown in the right. Net erosion is the same as uplift. And then you see that the colors indicate here that you have increasing uplift northwards, exceeding 2 kilometers uplift and erosion. And this means that if you put that back to the maximum burial, you see that the maximum burial has been different in these different wells. And this is important information because this is the one that goes into the Valderhaug modeling and controls the stiffness of the sandstones. And here you also have the temperature at maximum burial. And we see here that most of the area you are way beneath the 70 degrees, so you've been cooking the rocks. But some places actually you haven't yet entered the cementation window. Okay, here is an example from the Wisting Central well in the Hoop area, where we see that there has been, this was actually published in a recent publication, and it illustrates this approach that I just showed you. You have the burial curve here in the upper left, and you have the 70 degrees down here, and it turns out that the sandstones in this Wisting field has just barely dipped into the frying pan, and it's just a few percent cement in these sandstones before they uplift it. Almost like 1900 meters. And then you see how you can explain the observed velocity and porosities by doing that exercise as well, and the cross plots here. But more than that, you can then do the AVO modeling, doing this Monte Carlo simulation in addition, and here is shown as ellipsis, isoprobabilistic ellipsis for brine, oil, and gas. And you see that we expect a class 2P to 2 for oil here in this case, but you are very close to this onset. So if that uplift was slightly less, you could actually easily get an unconsolidated sand in this area, and then you will flip it to a strong class 3 immediately. So it shows how sensitive just a little change here is on the AVO responses. Brine sand here is a class 2P converting to class 2. Do we see that in the data? Well, actually, this is just a synthetic gather, but at least you expect to see that on the top of the reservoir here, going from a class 2P to a 2 in the oil zone here. And just to sum up that kind of importance of integrating the burial history with AVO is shown in this figure, where you have different profiles of burial history giving different AVO signatures. And this, over the Barents Sea for the Still, you will have variations of these, of course, even though these burial curves are for different ages, though. But this is kind of summed it up in one slide. Okay, and then we can do this this modeling, this combined rock physics and genetic modeling away from wells, along that, using the uplift map or the maximum burial map to constrain that modeling. And here you see burial curves to the left. Then you see the cement volume coming from the Valderhaug. The orange dots are at the maximum burial and the present day depth respectively. And then you see the porosity evolution, and then you see the PV velocity. So these are just modeled out in the space. So this brings you back to the map. You can plot this in the map view. But let's first also model the shales, because we need to have the shale properties for the AVO feasibilities. This we did empirically. These green circles are the mean values for one well, and we also split up into different shale intervals, the Collier, which is Cretaceous shale, and then you have the Poulin formation, which is on top of the Stir formation, which is the one I'm going to use actually now, and then a deeper Triassic shale, and then you put them all together. And of course, there is always some philosophy of how to fit these, and here they are compared with some also literature publications trends. We were uncertain whether we should use a power law or a linear regression. Maybe the power law gives best fit for the data, but it's also more risky if you go to other depths than what is shown here, because you suddenly get very low velocities. So we decided to stick to the linear trends. Could be that some of these shales are actually more, the deviations are more related to the positional changes within the shales than the genetic compaction trends. And these are things we're also looking into, of course. And then we can create these feasibility maps of rock properties for the shales and the sands using these modeling, both from the Valderhaug for the sandstone and the empirical one for the shales. And here you see that the upper left is acoustic impedance for the Caprock Poulin shale, and then the VP-West ratio for the shale in the upper right. Then you have the stir formation sandstone filled with oil in the lower left, and then the VPBS ratio for the stir formation with oil in the lower right. And then having that, you automatically also can create any AVO attribute at that horizon. And this is showing the brine AVO class for brine-filled stir over this region. And then you have the oil-filled. And here we assume the temperature gradient constant of 38 degrees. And what you see here is interesting, first of all, is that the AVO classes changes drastically even for one fluid. So the geology is really controlling the changes of the AVO classes, much more than the fluids. But there is also interesting changes going from brine to oil in certain areas, whereas in some areas there are no change. For example, in the fingertip here, it stays at class 1 in both. So you have probably a much stiffer, more cooked rock than in the hoop area. And then if I just compare the net erosion map here back and forth with this area, we see that there is really controlled, the information in the AVO plot is really controlled by the constraint from the net erosion map. So you're bringing in the geological information from the seismic velocities and the uplift estimation into the AVO domain, which and then that allows you to extrapolate and interpolate between wells. And that's a much better way to honor the geology than just do a pure interpolation between wells. Okay, so going next, here is just showing some feasibility maps comparing if you have constant temperature, and we actually modeled using basic modeling. We did some temperature modeling and see how that affected the AVO classes. And there are some interesting changes, at least locally, but the overall picture is the same. And then here is the application of this towards a prospect. So we select a prospect somewhere in between, and then we can also look at, here's the brine class in blue is class 1, and it's staying pretty much class 1. But actually, if you use the temperature, varying temperature gradient map that we had here, we actually see that there are changes going from brine with a dominantly class 1 to P to a more class 2 for the gas and maybe 2P for oil. So this is, of course, interesting to see that you can fine-tune and get into an area. It's more important to be correct in your properties and not just assume something. Okay, and then just I think it's a final slide or one of the last ones before I go to the conclusion, showing also we can use this to create silo wells. So here's a crossplot of P velocity versus porosity from the stir formation. The blue dots are the wells in the fingertip area to the left, and the yellow and the orange colors are just different wells in the hoop area. And you see that it's actually a big jump in the velocities, so they're completely different reservoir quality and stiffnesses going along that. And we did, having used this feasibility map approach to create different scenarios and silo wells in this for this area, you see that we are actually closer to the hoop area representative, but it's actually starting to move in that direction. So that's interesting. So you can use this to then de-risk prospects in this area in between. Okay, so just to sum it up, we have presented a novel technology to generate these AVO feasibility maps that can be used to de-risk prospects. And they allow for rapid extrapolation of expected rock physics properties away from well, which can be useful, especially in frontier areas or areas with few wells, but also in more mature areas where you want to go sort of off the cliff or away from a near field setting where you're going to go a little bit off the area of where most of the wells have been drilled before. And that also could allow for a more combined hybrid version of data-driven and model-driven approach. And this multi-scenario modeling is a good way to assess uncertainties and also address alternative models. And then a key uncertainties in this technology is the temperature history, of course, and we're working on incorporating the heat flow modeling into this workflow as well. Grain sizes are important because they also control the cement volume, and the sorting and the positional parameters. Heterogeneity is another one, and isotropy and overpressure and so on. The bottom line, I think, is that this workflow really requires a good integration across the disciplines, and we need to work across the silos. And having done this work with Spirit Energy, the one I showed you, it was really important for us to get good inputs from their geologists and geoscientists working in the area. And in the future also, we're going to look how we can use this as an engine to build augmented training data for classification of AVO inversion data. So with that, I would like to thank my co-workers at DigScience, Ivan Leoski, Tor Jansen, and Christian Angai for good contributions. And again, thanks to Spirit Energy and Partners of PL 962 in the Barents Sea for data and financial support. So with that, thank you very much.